In this little presentation, we will talk about conjugated systems yet again and their synthesis and reactions specifically. So the synthesis of conjugated systems. Now this may or may not be in your textbooks, whichever one you're using, but I just want to review this for you because I mean it's not new, but still. Okay, so if you want to synthesize any kind of a conjugated system, then you would do elimination reactions. Essentially, all conjugated systems or isolated systems, they're all double bonds or triple bonds. So the way you make alkenes or alkynes is by elimination reactions. So you would start with anything that has a good leaving group, for example, bromine or chlorine, and then you will do two eliminations in order to end up getting a conjugated system. So the way your bromines are arranged will dictate what kind of a product you will get. Okay, so for example, both of these compounds, if you do elimination on them, you will end up getting this conjugated system, the butadiene. The way you make these brominated compounds is of course from alkenes. Okay, you take an alkene and you brominate it and you will get the dibromo compound, and then you do the elimination. So and since these are straight chain compounds, remember you have to use a bulky base or something big and strong in order to promote elimination. You can also start from an alkene like cyclohexene, for example, and you can add bromine in an allylic position. Now remember, the allylic position is the third position from a double bond. So 1, 2, 3, or 1, 2, 3. So the third position or the third carbon from the double bond, the start of the double bond, is the allylic position. So you treat that with NBS, and you must have heard of this reagent before, N-bromosuccinimide. And so you treat that with NBS and you end up getting a bromine at the allylic position. Once you do an elimination with a strong base, this is the only place where you will get elimination, okay, or a double bond. So again, this is how you would form a conjugated system. If you wanted to form one more double bond, you could do one more NBS and do one more elimination, and you form a double bond right here. So you can keep going on and on and on, all right? But anyhow, that's how you would make conjugated systems. If you wanted to make long chain conjugated systems, that's what you would do. You would start with a long alkene, okay, and then keep doing allylic brominations, eliminations, and so on and so forth. Okay, so let's look at some of the reactions then. Essentially, there is only one reaction that we can do on any kind of an alkene, and that is an addition reaction. So in a conjugated system, things are slightly different. However, things are also similar. So for example, the double bond will undergo electrophilic addition. And what that means, of course, is that you're adding an electrophile to the double bond. The double bond is the nucleophile. So this is a very common reaction that you have done before, where you take an alkene and you add HBr to it, and this is how it will add. Okay, but when you do it with a conjugated system like butadiene, you also get one other product, okay, which is this one. All right, so when you start numbering this versus that one, you will see that the first one is a 1,2 addition, so which means hydrogen added over here, which is typical of the Markovnikov addition that you will have. Hydrogen goes to the carbon with more hydrogens. So that's the Markovnikov addition, and then 2 is what the traditional one would be. However, this is a little bit non-traditional. So here you have a 1,4 addition going on. So the hydrogen added on to the first carbon, no problems. But then when you were expecting the bromine to be on the second one, is really not on the second one. It's on the fourth carbon. So something has happened, okay, going on. The other thing to note over here is the location of the double bond. In case of the 1,2 addition, the double bond, the second double bond that we had, stayed the same, okay, it did not move. However, in the second case now, the double bonds changed. Okay, it's not in the same location as it was before. Anyhow, so we will have to talk about this. Okay, however, I just want to give you the nomenclature of this. The first product over here is called the 1,2 addition product, and the second one here is called the 1,4 addition. And this is a very traditional thing that happens when you have conjugated systems. Okay, if you had an isolated system or if you had a traditional alkene, this would not be an issue, but we are in conjugated system, so we have issues. So there is some resonance going on, okay, which means we have to look at the mechanism of the reaction. And so there is some reaction going on, there is some resonance going on, and there is an intermediate that's formed during the mechanism, and that would be the allylic cation, okay? We'll see in the next slide. So then what happens is that the nucleophile will add to the second carbon or the fourth carbon, all right? Remember, the first addition is the nucleophilic one over here, the electrophilic one, and the second one is the nucleophilic addition, okay? And so then the Br can attack on the second carbon or the fourth one, and how that happens is on the next slide. So here we are, okay, we'll take butadiene and we add H to it, and of course we're adding HBr, okay? So the first step is adding the hydrogen ion to it, and or you can just say that the double bond here will attack the hydrogen, and here is the hydrogen, the extra hydrogen over here, so which means you form a cation on this carbon, okay? Remember again, this is Markovnikov addition. That does not change. So here's the carbocation that's formed. Now this moiety over here, okay, this intermediate over here, this is an allyl cation. We just talked about allyl additions, and I said the third carbon from the double bond is called the allyl carbon. And so here this is an allyl cation where you have 1, 2, 3. On the third carbon you have a positive. So what happens now with this intermediate is that you will get resonance, okay? And so that's why I have these arrows here in yellow, so you can kind of differentiate between reaction arrows, mechanism arrows, and then of course the resonance is very clear. But this is what happens. The double bond moves from here to this location and creates another carbocation, which is this one, okay? And so these two are in resonance of each other, and these are the allyl cations. Now one may argue and say, well, this is going to be more stable. This is less stable because of the primary carbocation. This is a secondary carbocation, but that's not how you look at an allyl cation. Okay, in an allyl cation, you have to look at the resonance structure. And when you have resonance, you also have delocalization of electrons going on. So here the double bond is then shifted all over these 3 carbons. This is how it's distributed, and the positive charge is also distributed over 3 carbons. So distribution over 1 versus 3 is a lot. 3 is a lot better than 1, okay? And so allyl cations are very stable. You cannot look at it from the point of view of secondary versus primary, okay? So here we have resonance structures forming. So at one point you have the carbocation here, which originally that's where it was, and in the second case after resonance is where you have the carbocation here on the fourth carbon, okay, from the original, from the first carbon, the fourth carbon. So then in the second step, when the nucleophile comes and it attacks, it can attack on 2 locations. The one is going to be here, which is the second carbon, that is the 1,2 product, and then the second attack is going to be on this carbon, which is then the fourth carbon from the first carbon that had the hydrogen, and that is the 1,4 addition. Now, these two over here, these two products obviously are different, okay? And chemically also we call them different, all right? So 1,2 and the 1,4. There is another name for these two, okay? And the first one, the 1,2 addition, is called the kinetic product, and the second one is called the thermodynamic product. The kinetic product is always going to be 1,2. The thermodynamic product is always going to be 1,4. The kinetic product is always going to be formed first. The thermodynamic product is always going to form after resonance, okay? Those are the key things of conjugated systems and kinetic versus thermodynamic products, all right? Now, here is the kinetic product, all right? And here is the thermodynamic product, which is 1,2 versus 1,4. The 1,2 formed faster. This was the kinetic. That's why it's called kinetic, because it is based on speed. And so this formed faster, so it has higher energy, okay? Whereas the thermodynamic product formed after resonance, and therefore it has a lot less energy, okay? Which means it's a lot more stable. And here is the intermediate that I was talking to you about, where everything is delocalized over the 3 carbons, okay? So essentially, the kinetic product is higher in energy, thermodynamic is lower in energy, so more stable. So if you give it enough time, then you will get the more stable products. It's kind of like relationships, okay? You know, falling in love at first sight, whereas giving relationships some time, and then you have a more stable product. If you give any relationship some time, you will get a more stable relationship. That's exactly what this is. The other thing I want you to note over here is the temperatures. Okay, before I move on from this slide, the kinetic product was formed at a much lower temperature. The thermodynamic product needs a lot more energy, as goes relationship, right? All right, so here we are, major product at 40 degrees centigrade, and that's when you get the more stable product, the thermodynamic product. The major product that you get at minus 80 degrees centigrade is the kinetic product. So the 1,2 addition happens very fast at lower temperature, whereas the thermodynamic product happens at a higher temperature and after resonance. And it's the 1,4 and it's the more stable product. That's what this entire slide is about. So continuing on, just to make sure that you kind of understand that you will always get two products, okay? Whether you do your reaction at a low temperature or a higher temperature, it doesn't really matter. You will always get two products. Their ratio is going to be different, okay? So which means that whenever you have to answer these kind of questions in an exam or assignments or wherever, you want to make sure that you write both the products out and then indicate which one is the major one, unless, of course, the question is saying just give the major product. Okay, that's all. So then you only give the major product. In that case, you look at the conditions. So in the lower temperature conditions, the 1,2 or the kinetic product is going to be the major product. And at a higher temperature, the 1,4 or the thermodynamic product is going to be the major one. Okay, but otherwise, you will always form the two products. A little bit about allylic cations and radicals, okay, since we are on this topic and we are talking about resonance and all that. So really quickly, you can form allyl cations, and you may have done this in your organic 1 when you were doing addition reactions. But anyhow, so once you have allyl radicals or allyl cations, okay, they're very, very stable cations, okay? So for example, a primary allylic where you don't have any substitution on any carbons, it's almost as stable as a secondary carbocation, and a secondary allylic where you have substitutions on carbon, which means you have another methyl group or ethyl group or something, then those are as stable as tertiary carbocations. And in some cases, they're even more stable than tertiary carbocations. So allylic radicals and cations are very, very stable. Okay, so the radicals are the same way. This one shows for the this resonance is for the cation, but you can draw a similar one for radicals also. You'll just have a half-headed arrow over here. So it's a very common thing. So when you have these kind of double bonds and such reaction possibilities, you have to note whether you have an allylic substance or not. So just to review a little bit here with you about the allylic bromination, you've done this before, but as we just said, bromination occurs in the allylic carbon, and the mechanism is by free radical. I'm going through this again. You've done this in organic 1 most likely, but we should talk about it again because we'll be doing a lot more synthesis in this course, and so you kind of need to know how to manipulate molecules. Okay, so the mechanism is by free radical, which you know is using light, okay, or energy, some sort of energy. Here is the mechanism for this kind of a reaction, especially for allylic bromination. And you form a free radical right here, abstracting this hydrogen. So the free radical that is formed here will undergo resonance and form a free radical here also. Okay, so this is a resonance going on. And then the bromine will come in and attack on the free radical. That's where it will add. So, or excuse me, this is a substitution reaction. So this is where it will substitute. In this case, both of these compounds are the same. This is the allylic position here, and this is the allylic position on this compound, but they're both essentially the same, okay? But they will not be the same had there been a substituent over here, a methyl group. Even if you had one methyl group over here, that would have changed the nature of these two, okay? So which means you would have had two products, and that is because of resonance, okay? If there was no allylic position possible, which means if there was no double bond, you would get only one product. But because there is a double bond present, you have generated an allylic position, and because of that, you end up getting two products, okay? And typically in organic chemistry, you will form allylic products or this kind of a bromination using N-bromosuccinimide. So I talked about this in the previous slides before when we were doing synthesis. So N-bromosuccinimide is a very, very common reagent that you would use here. So instead of using HBr to do this addition, you would actually use NBS. Okay, and so there's a constant production of bromine in here, and so that really promotes this reaction. If you see NBS anywhere, that's all you're doing, allylic bromination. So that brings us to this little portion of conjugated systems. So please note kinetic and thermodynamic additions. The one that I did here for you was just for butadiene, but it doesn't mean that that's the only one. You can have hexatrienes, you can have cyclodienes. So you have to practice reactions and writing reactions for kinetic and thermodynamic products for all those kind of addition reactions. You must write out the mechanism of the reaction and write out the resonance structures that you will get. And then of course, remember that NBS will give you allylic addition. Okay, this is a very interesting reaction and very useful one too, for that matter. Okie dokie.